Okay, so we have taken some data, we've made some concentrations, looked at some cool viewing. Um, Probably the last thing we should do with this data set here will be to look at the raw XRF data and go through how we would fit that with PyMCA to actually do our fitting properly. All the data that have been in these channels so far have been the bin data, which, for 95% of what you want to do is sufficient enough to go through. But if you do have any overlapping peaks, K alpha, K beta things that are confusing, or if you have a lot of scattering background, you may need to go to PyMCA to remove those effects. So let's figure out how to do that. So here we are on our JR data again. One thing we might do just to verify that we would want to do this, so we can look at the correlation plot. Of course, it's down below here again. Let's move it back up. There we go. And I can plot iron and manganese. And the question here in this plot is how much of that manganese is due to iron swelling overlap and filling the manganese window. So how much of that is really true correlations versus problem correlations? So normally when we do this, I didn't put in the entire massive MCA data file, but you will see typically what we do is we go to MCA spectra, and you get your MCA data in a lovely zip file, tar.gz. You need to unzip it, extract it, find your data file, unzip it again. It's nicely buried in a few levels usually. I know it's annoying, but it's actually the easiest way to do it. And you would go to construct and express 3 HDF and click on any one of the lines, because the data files are you get one line of data per line of your map. And so you go and construct that and add it all together. And once that is done, you can say define MCA file and look at your data. And I believe we've already done that first bit for us today. Otherwise, it just gets too ornery. Yeah, so here we are. And you get something like this that says like your file name and MCA. And you can select and open that. Now, the other thing is that those files can be fairly large, and they add up after a while. The other thing you can do is set the HDF write compression. The default now is gzip9, which does a pretty harsh, pretty strong compression. And so you can take about 400 megabytes of raw HDF5 maps down to about 10 megabytes of single data. So I recommend, and it gets rid of all the extraneous garbage in those files too. So I recommend using the compression. Okay, so we've defined that file. And now, as you remember, if I double click on a map, you do get, where did it go? Here it is, sorry. The XY profile, if you remember that, right? I can either do it through the menu bar here, or I can right click on the map here. Get the map. We can say view MCA. If we do the view MCA, and I double click anywhere on our image, you get your profile there, as well as, let me bring it up to the top here, our MCA spectrum at that point. So there is that 1 pixel's MCA spectrum. Now 1 pixel is great, but again, these are typically at maybe we're clicking at 10 milliseconds, maybe 50 if we're going really, really slow. And that's what, a really slow, really fast data collection might look like. So we can get single points that way. If you remember how we were doing masks earlier, and we drew a mask this way, right, using the shift. The other option in that ROI selection is MCA. So if I choose not to make a mask and I choose MCA, you can also do both, do MCA and mask if you're so inclined. It'll now, instead of showing you the pixel, it'll show you the sum of all those pixels, the average of those pixels there. And now it looks, instead of looking like a really, really noisy MCA spectrum, it looks like, oh, that looks like something I could actually analyze, you know? I see peaks. You have the option under the MCA menu here, the sum option. So right now it's going to average when you do a mask like that. If you prefer the sum, you could choose the sum. It'll look just the same. It's not going to change the smoothness of the data. It'll just change the magnitudes. So that's what that does. So now we have our lovely spectrum. Now again, our background looks pretty nice here. There are things you can do. One of the things we might often do is rebin the MCA data. So if you don't want to do a full pi MCA fitting, but you want to fit a range of what you think that peak is. So we could say, I can even come down here. I'm going to join the little zoom button here and scroll down in this low area. We could say, okay, you know, one thing I didn't window was the argon, you know. I'm really excited about argon in my sample. I'm not, don't worry. But say I really wanted to window that, you know, because I think that's really important for some strange reason. So I could zoom in on that and I could say, let's rebin that MCA to the data. And I would pull that window up from here. And I would choose, say, I wanted to go from bin 270 maybe to 310. And maybe I make that a little bit lower here, a little higher here, lower here. There we go. And I say, oh, I can't wait to see what my argon looks like. Hit OK, finishes. And you're like, great. Oh, argon's everywhere except for scatter. OK, so it's not very exciting as it turns out. I know we're not shocked by this, but so I haven't made the name generic because I started out with X-ray data, since this was X-ray starting with. And MCA is kind of our full spectrum information. But generally now, any of the hypercube data that you're going to work with, whether it's mass spectrum, infrared, UV visible, all goes through this MCA spectrum viewer. And a lot of the principles are all the same. We can load the data in, do all these things with it. If we get down to some of the multimodal aspects of that, we'll show some of that today as well. And there's, you know, there also are a couple other things here. So notice here we've been working in bin number, which is, you know, very exciting and everything, but not always useful. We know that in general for most of our detectors, it's 10 EV per bin, so this is just around 3 keV. If you're really one of those people who really needs to work in EV rather than bin, under the MCA view, you can say I'd rather work in spectrum mode. Now, this asks if you want to use MCA in the data file. If it's present, this would be if you have FTIR data or mass spec data. It has its own access for that. Since we don't have that in our data, we have to say no, and we say, let's do this with 10 EV per bin. And yes, and now you're in EV energy. You could also, you know, if you prefer KEV, you would say 0.01, and you get KEV. And now you can also now work in, I'd like to rebin the MCA using the value axis. That means working in whatever axis you are on here that's been converted to spectrum axis. So if you prefer working in whatever value that numbers that are, be it wave numbers, inverse centimeters, nanometers, EV, you can work in those if you prefer rather than bin number. If you're too lazy to figure out what peak you want, you can also say, let me just rebin everything. So you can say rebin MCA ranges. And you can say starting at, let's start at bin 200 and go through bin, let's call it 1500 then. And I want to bin every 50 bins. And it goes through. is now binning all of your data lovely for you. And here they are. So these are all working in bins now. And you can take a look at your data and go like, woo, there's things happening, yay. Now you're in scatter. And so that's, that does work. We can try a new feature here if you're so crazy. We can, let's see, where is it? We can save our displays as an animated GIF. If you want to make a cool action GIF of your spectra. So we're going to do that. And okay, it's down here. So we bring that up here. This is a brand new feature, so it's probably going to fail on me because this is the first time I'm showing it in public. But let's see what happens. I'm going to select that entire range and say GIF it. Oh, it's working so far. And now, oh, and see, it just crashed on me down here. I knew it. I know. Okay, I'll fix that quick. Anyways, we'll save the GIF. And that can do fancy things. It did work at one time, I swear. But that can do things like that one. So that's stepping through, in this case is mass spec data, but stepping through every mass to charge between 100 and 325 M to Z. And so if you want to see how, it doesn't give you a scale or anything there, but you can kind of see, oh, look, there's a whole bunch of stuff that happens here. You can see different flashbacks of different parts of the sample lighting up. So it is kind of cool. So things to think about one day. Once I fix that bug, I'm going to add that into my open bug report here. So now we can go back to this, and now we can even look at how we can actually fit these peaks and get the Pi MCA fitted data out of it. So we'll start this by going to viewing the configuration screen. And again, this is another giant screen, so I apologize to those of you with tiny laptops. It's even big for my screen. We used to have this all on a tabbed page. It was a little bit smaller, but it got to be really hard to navigate on the new Macs, so it's all on one page now. So we have a periodic table that's going to describe the peaks that we're working with. We have the fitting region and some of the fitting parameters here. Let's see if I can get to that bottom bit a little bit better. I can just see the scroll bar on mine. Maybe. So here we go. And there's the rest of it there. The most things we're going to use the most here are going to be this left side here, though. Okay, or the first couple tabs. So let's clear out the defaults here, and we're going to say we're going to integrate everything from Argon and above. And so we're going to ignore Argon and go from say 310 to 1200. It's already read the incident energy of our data set from the information, so it puts that up here. One of the major problems that people will have when they're trying to do this is they'll fit it and they'll throw some air about not being able to fit a peak. And that's because they're trying to fit uranium on this data set, and uranium's not even being excited. And so if you're trying to fit an edge in a line that's not excited by the incident energy, it's going to throw up an error. So make sure that, and this is the most important when you're doing, say, a multiple energy map, and you're, say, going through the iron edge, and you're mapping out a few energies that are kind of around the edge value, but not fully above it. It's going to yell at you for not having any iron in it. So you just need to put the energy and say, it's at 8,000, who cares? But just fit my peaks for me. Bump it up. So we're going to start with potassium, and then we just say K edge, please. Calcium, K edge, titanium, K, chrome, K, our best friend manganese, second best friend iron. We might see if there's any cobalt in this one. Normally we always ignore cobalt because it's right on the beta of iron, but we'll try to see if we can pick anything out. We're doing the Pi MCA version, and we'll go up to zinc. We don't want to stress it out too much, right? And there we go. So there's our peaks. Our range here is okay. We can do some things where we want to average the data points together to get better fitting results, but I tend to avoid that for now. The very first time we're going to do this, we're going to leave all these variables to float. So I'm going to unclick the fixed value, and we'll let it try to calculate out our pileups and other factors in there. And the very first time you do this, everyone always fails, and they go, it didn't work. And so we have peaks here. We move to parameters. And the one thing you will need to do, I almost guarantee you, is go over here, over here, right there. Come on, don't go down there. There we go, is to the attenuators page. And right now, it needs to use what the detector is absorbing, and it has nothing in there. And I guarantee your detector is actually made of something, not a double line. So you need to go down here and select typically either silicon or germanium. I have a silicon detector on mine, so silicon. That will be the most important failure you will get if you don't fill that in. Okay, that's all I'm going to do on this page for now. I'm not going to go to the App Store. There we go. We'll come back over here. And now we'll come back to our main thing here, and we'll say fit current. Hopefully this will work. It did. Look at that. And there's our data. I can go to view, and I'm going to go to a log scale to see all my tiny peaks. There we go. Fit current again. And there's the range we're fitting. And it's, it does a pretty good job. We probably need to do some extra fitting to see if we can get some more width here. So we can fit again. We can see that our detector width is getting a little bit broader. It's getting a little better, maybe. It's kind of zeroing in. It does a pretty good job of characterizing what we're looking at there. Could be a little bit broader, maybe, but that looks about right. It's going to be dominated by trying to fit the air around this peak here. This could be just a little bit of background, so we could do some other background tricks, but I think we're going to leave it as it is. When we feel pretty good about our base MCA fitting, we're going to go and fix these values because we don't want the fundamental detector parameters to vary in our fit. So we'll fit those, we'll fix those. And then we can come to our map here again and say fit all or fit zoom. If you fit all, that'll fit your entire map, which is normally what you want to do. Back in the day when this was a painfully slow experience, you would leave and go out for dinner and maybe a couple glasses of wine and come back and it was still working. You might even just do the area you only cared about and so you say fit zoom. Luckily though, it does go faster now, so we're going to be courageous and say fit all, and it will go through and fit all the data. And it'll spin like that for a while. We have this lovely button here called Save Config. Now we have new channels here that have, say, the potassium channel, and you get a sigma channel. And so the fitting that it does here gives you an error bar. So this is basically a small error bar for every one of these as well. And so you can see if it found errors. So there's, oh, that's why. I remember why now. That took me a minute. So we're going to notice here that we have a high error bar on titanium. Right? You're going to be like, huh, I wonder what that is. We'll talk about that in a minute. We'll come down here and you say, okay, chrome, okay. Sometimes it's just high because you have a lot of concentration on it. You can kind of see some of those areas. But it looks pretty nice overall. We're going to take a look at this real quick, though. I'm going to pretend I'm really worried about this titanium peak. Kind of actually am, but I remembered something just now. So I'm going to zoom in over here. I'm going to use our, we picked some random area around one of the more intense regions, right? Well, what does this region look like? We had a lot of air here. So I'm going to zoom on this guy here, use our shift select, and I'm going to choose the MCA down in my lower window here. And there's our updated MCA, right? I can say fit current using our current parameters, and notice that, oh, look, we're totally missing a whole peak right here. And you may decide that, this is a really tiny peak, that doesn't matter, but maybe you do care about that. And you can go like, well, what in the world was that going to be around 5 keV or so? And now I'm going to switch my selection to L edges and choose barium L and fit current. And there we go. And it does a better job on that. So I'm going to unfix this again for a second. And fit. And you can see that was a bit of barium sneaking in on that peak there. And now you can go like, oh, well, I just fit it though. What am I going to do? And you don't want 1,000 channels in your data all the time, right? I get annoyed by that too. So I'm going to say, okay, that was a good first fit, but now I got a better one. So I'm going to remove a whole bunch of channels. Come down here and bring that up here. And I'm going to remove that first set of fits. And that starts from here and goes up to about here. Say, okay, get rid of those. And now let's fit everything again with our new parameters. But yeah, the save config is a really good one. And I often will do that even for, say you're fitting say 3 or 4 different types of samples you fit, right? You can say like, this is my nickel battery fit parameters. I always have all my major ones for that, right? Even though you may change some of your number parameters here, your elemental parameters will be the same. That's can save you, a little bit of carpal tunnel in your finger by the time you finish selecting all those K edges by the time, of all your elements, right? And now we can say like, oh, look, was that really barium? Like maybe a little bit there. So maybe I was much ado about nothing there, but there's still titanium, maybe a little bit of air there still. Maybe it got a little bit better. But now let's go back to our first question that we had, or we thought we had, at least. So here's that iron manganese curve. Let's zoom back out. Clear. And we'll do our edge zoom. So that was iron and manganese. What does iron and manganese look like now in our true fit? Here's iron. And here's our manganese. It looks similar. You see, if you notice the background's a little bit lower, because that background of iron K was leaking into the manganese window, so that base slope is now a little bit flatter. What I often like to do to see if this is all worth my time often is now look at iron versus iron, right? So let's see, maybe I still have one more edge leakage here. Edge. Yeah, there we go. So iron and iron, not many interference with iron. It's a lovely straight line. So the iron bins that we made were pretty much true. What else do we have? You could try to see, did we have any cobalt that came out in our maps? Maybe some real cobalt was here. Big error bar on the cobalt too, but we'll see. We'll take a look at that in a minute too. Our question came down to manganese, of course, though. So here's our manganese, and here's our manganese. And you can see, oh, wow, look. So there was one area. In general, it looks pretty good. But there's one area here where we had much higher manganese than in the bins than the fits would produce, right? And now if you remember, we can say, well, what area was my problem area? What area was I about to misinterpret? Draw that little box here in our zoom. And go to manganese. I'm gonna go to log scale so I can see everything. Oh, there we are using the mask. Ignore, use. And so that's our area. So all those chromite grains had manganese in there that probably was either due to the high iron leaking over or the chromium leaking in. It's the beta from chromium coming in. So you can have those kind of fun bits there to really tell out. So the manganese is definitely worth a reinterpretation. Now we can also ask the question, is that manganese, how much of that manganese is real? We'll start with the iron. So we'll go to iron. And I'm going to plot the iron versus the iron error bar, so the iron sigma. And it should look something like this. So based on Poisson statistics, so photon counting, the error on the number of counts should be related to the square root of the number of counts. If you can't see that on the line here, you can't do that in your head. I can't always do it. If you go to error and say, show me a square root line, there you go. So all our data follows the Poisson statistics. So we can trust all the iron data for the most part. That's nice. I like that. Can I trust manganese data? I can up to a point here, but there's these little bits here. There's a little bit more error, right? So the manganese that's in that chromite grain has higher error than I might expect. And that's okay too. And this tells you where you might not be able to fully trust all your data here. Yeah. How about the cobalt? Do I trust cobalt data? It's all present there, but it's all present at an area that my error bars are higher than they probably should be a little bit. So just be aware of the error bars on them. So I mean, it's still within the error, 200 counts plus or minus 15 there or so. But the error is higher than the Poisson statistics should be. So there's extra error probably due to the overlap of iron and cobalt in the fitting there. What you really want to make sure is that your data is not like so far outside of these lines here that you can't trust it, that your error bar, your sigmas are so large. At any point here, I can always go to File and export all that data.
You can save that as a PDF.
Yeah, I can always, let's see, I don't have a save plot action here, but I always just do screen captures at this point if I want to save it. Of course, at this point in time, when you've gotten to that point, you want to save process to make sure that everything is good, save your data sets, and feel happy about it. So ignore here. So I'm just gonna make some arbitrary stuff here real quick, right? So here's a mask. Boo, boo, way here, yeah. Oops, nope, not a line. There's one, right? And we're gonna come here and say view, process, sorry. You'd think with these categories, I would know where things are, but I still forget. Create new channel for mask, and we'll call this ROI. And we'll come back here again. We'll make another one over here, right? That's a beautiful one. I'll come down to my ROI channel again. I did the other one. I didn't click on the right button here. Sorry. Mask. All these things are hidden underneath here. There we go. Use mask. Okay, so we're gonna have one that's here and one that's all over the place. So here, process, add mask to channel, ignore. So now I have this mask, convoluted multiple ROI areas here, right? What I can do now is come back to process now, and if I say use current channel as mask, it uses any value greater than 0 as my mask point. So there's my current channel as mask. If I come up to barium here and I say use mask, notice that's both masks, all the masks combined together. And if I wanted to flatten that mask, I can now go to, once again, to process, create a new channel from the current mask, and this is my flat ROI. And now I have a flattened ROI, all ones, just of the one region now, all disconnected, all put into one. We can go to workflow, and I don't have a predefined one here, but we can go to the workflow editor here, for instance, and bring this up here. And we could say a new script, and this would be, you know, fit MCA data. Right, and we could add a command, and the first command might be to go to Analyze in the PCA menu, and the operation, oh, no, not PCA, sorry, MCA. Too many things that end in, pi MCA even was what I want, right? And I could load a file that is my, whatever the name of, like, you know, my favorite MCA fit that you saved from that save button, right? And then we could add another command that would be, again, analyze pi MCA, and operation full fit, right? And then you can just save these scripts here, and then it pops up in your queue here, and now you have that script in your data from now on. I do recommend, if you create a new script and you want it to be saved, is that you say save workflows at the end, and that'll resave your workflow file. If you spend all this time making a really awesome workflow, and now you want to send it to your friends, because I'm trying to really encourage this, right? You can export your workflow. It'll save that little workflow in a little JSON file. You can import it when someone else sends you a really cool workflow too, right? And you're all good. And I also would really encourage people to go to the support forum on samsxrays.com. And if you have something cool, share it to the group. And people go like, oh, I really wish I could do that more often. Thanks, I never thought about that workflow before. And the idea is kind of at least share the ideas of how you're processing data together. As I get actual things documented, I'll start putting workflows on there too for things I recommend